Yeah. Okay. Okay, then I think let's start. Welcome everyone. So, I'm Sanchayan, uh, and we are doing this meetup online for the first time because of various situations, and we are doing it with conjunction with Anupam, who runs the FPNCR group out of Delhi. So this is a kind of joint online meetup with, I hope, various people from various places. So what I will be covering today is lenses, and the agenda will be something like I will cover some examples from the Optics by Example book by Chris Penner. I will be mostly walking through them, and I will try to cover this in like 30 minutes or so. And then also we will have questions in between if anyone has them. And after that, what I will move on to is the underlying, let's say, construction or how exactly Lens works. So, just a disclaimer, you need not understand how Lens or any of this works in the background just to be able to use it. So, if the part after the first 30-45 minutes seems tough to you or it's something scary, don't worry. That is not something that will come in the way of just using it. Is someone saying something? Quite a bit of static. Mm. You can also, if you have some questions or something, you can also use the chat window to your left. I will try to keep an eye on that to see if anyone has questions, if especially if their mic is a bit problematic. But otherwise, you can just interrupt me in the middle. Okay, so let's get started. So what I have here is I have some Jupyter notebooks, which has the various examples from the book, the Optics by Example book, and I'll be covering them. I will share the link on Telegram group at the end of the meetup and also on the meetup event page. So you can always access that. Okay. So let's get started. So first things first, why are we even considering this? So first of all, what is the optics in the first place? So optics has various, I don't know, let's say various stuff for the lack of a better name. Lenses, folds, travels, and prisms and ISOs. Today, I will be mainly covering lenses. Folds, traversals, and prisms will cover later on. Uh, and just note the library in Haskell is known as Lens by Edward Kemet, but it actually has everything: lens, prisms, ISOs, traversals, and a whole bunch of other things. So today we are only covering a small portion, so which will be lenses, and that's to get started with. And now, why are we even covering this? So the very common example drawn is in object-oriented programming. For example, whenever we need setters or getters, ignoring whether you have private, public, and all that. Basically, if you want to access nested members, all you need to do is something like a.b.c or .d, and you can basically access any member or set any member that you want. But Haskell being immutable, and since we focus on composition as such, what optics are about is basically having a functional getter and setter. So the getter and setter part we need primarily because of the way Haskell is written. Haskell records work or the immutability of the language. And the functional part comes from the fact that any of these things that you see, they are actually composable. So you can, let's say, compose a lens with a fold or a traversal, and it will work out to something, giving you a particular feature. So they are primarily functional getters and setters. And the reason we need them is, if you have ever worked with Haskell record types, trying to do something which you can easily do in object-oriented languages becomes quite a bit of pain, and lenses kind of makes them pretty easy to work with. The downside is, if you get type errors while working with Lens, they are a bit hard to grok. It's not quite easy to understand them upfront. So that's one part of it. Implementation, unless you are interested, you do not need to know. So maybe depends on how you say it. And then there are quite a vast number of so-called combinators. So you will see what combinators are in a little while. So let's get started with some examples as to what lenses can do. Now, just a word of warning, I am not well versed with folds, traversals, and prisms, and the examples on this page cover a composition of them. So maybe I do not have an explanation of each example that works, but you can still see what lenses can actually do, and it's pretty fun to walk through. So let's see. So a simple example can be, you have a person type who has an address and country information, and if you want to pull that out, you can use those. These are basically lenses. This will make a bit more sense once we get to the next part, and then you supply your actual structure you want to work with, and let's say that gives you Canada, something like that. Or you have a tuple like this, and you want to change the third member of this tuple to false. You call set. This will work on the third member of the tuple, and this will be basically set to false. Now, as I said, the beauty of lens is they compose. So here comes the first example. So what this example does is, we have a list of three tuples, and what it does is it focuses on the second part of the tuple, checks if it's a left, and kinds of unfolds it. And after folding it, it sums it. This folded is coming from folds, so this is not this is not exactly a lens. But if you do that, you can see the answer is 30. Now, if you look at the exact example, so we have left 10, this is a right, and this is a left 20. So what this did is, it took this, it ignored this, and then inside the two lefts, it focused on the 10 and 20, and it summed them. So you got a 30. So that's the way it worked. And this is coming from folds. Now let's look at a traversal. We have a list like this, which we are passing here. And what we are doing here is, we are calling this over from lens. It takes a function which can modify what you want to work with inside the storage structure, and then it basically runs this. So what this does is, it will walk through the list, it will filter, meaning it's filtering, and it's filtering on this condition that if these any of this has a length greater than 10, then only take it, and if it is, then apply this function. So if we see, we get this. So you can see that nuff said has a length less than 10, so it hasn't been touched, and the other two are modified. Going on to the next. This one basically capitalizes each word in a sentence. We have a worded, we have a head, and this is the combinator, one of the combinators that I was talking about, and it applies this to upper function. So, and it comes out like this. Sure, you can do it without lens also, but it's nicer. Then we have, let's see the next example. We have multiply every integer by 100, no matter where they are in the structure. Uh, can you hear me? Okay. Uh, I'm not sure how Jitsi automatically muted me.
Yeah, but you're audible now.
Okay. Okay. Cool. Sorry about that. So let's get back. So we were here. That's where we got out. So the next example is summarizing a list of numbers, subtracting the lefts and adding the rights. So some are folded beside negative and ID, and we have a list of lefts and rights. So it's only
Sanchayan, are you sharing your notebook? I don't see the notebook anymore.
I'm sharing the full screen. So okay,
Oh,
let
maybe
me.
my
Yeah, reload.
notebook.
It comes up.
Is it visible now?
Okay, yeah. Go ahead. I think it's just my screen which is frozen.
Okay. Uh, okay, then I'm going ahead. So what this example does is it adds the rights, subtracts the lefts, and if we see, we have got 27, which is that should be 10 plus 20 is 30, and then minus 3. I don't think I can write a quick function for this. Then we have another one where we capitalize each one in a sentence. Worded. So worded is basically going to split this sentence into each word. We are taking the head, and if I remember correctly, this is the infix combinator for over, and it applies the to upper function. So this is what we get. Coming to the next one, biplate. This actually is comes quite a bit later, after traversals and prisms. So I haven't really reached there. I don't have even idea how it works. But what this one biplate does is it multiplies every integer by 100, no matter where they are in the structure, and that's what we get. Then the next one, reverse the ordering of all even numbers in a sequence. So that's what it is. I don't know what parts of does, but traverse is basically traversing, walking through the list, and this is the filter condition. And then we are doing the reverse part. Then sort all characters in all strings across word boundaries, which is here. Then this one, flip the second bit of each number to a 0. So walking through all the elements of the list, bit at 1, uh, and then applying a not to it. So 3016. So 1 should be 0001. And then if you set the second bit, that becomes 1, 1. So 3, 2 is basically 0010. So setting that one to 0 makes it full 0. For 3, we have again 0011. So setting the second bit to 0 makes it just 0001, which is 1. And then 4 is your 842. Considering 8421, it's 0100. Setting the second bit means 4 and 2, 6. And then coming to the last one, prompt the user with each question in a tuple, and then return the tuple with each prompt replaced with the user's input. So it can even work in IO situations. And when I had run this, so in the end, this is what I had got. So these are some of the examples which the books gives to just pique your curiosity as to what it can do. Some of them are crazy, like the biplate one, but pretty interesting. So that's just to give you an idea of what the various repertoire of the library can do in different situations. So now let's move on to actually how lenses works. Before I do that, anyone has any questions, or is everything going fine so far? Okay. So I'll move on. So as I mentioned, optic actually has different things. We are only focusing on lenses today. And each type of optic basically comes with a set of compatible actions, which only makes sense with that specific optic. Then coming to the lens. So lens has a few properties which you must always remember. There are such specific properties for each of them. So in case of lens, a lens always focuses or selects a single piece of data within a larger structure. So for example, if your person record type has a name and an address and a phone number, it will always select only one of them at a time. So it will, depending on the lens, it will always, let's say, select the phone number or your name. It will never give you two selections. Then a lens must never fail to get or modify that focus. So a lens type can never have a return of a maybe. So it always must give you something. So any member of the structure you will always get as a result. It can never have a return, let's say a return type of a maybe. You cannot have a nothing. A lens must always give what it focuses on. So the very first sentence mentions optic comes with a set of compatible actions. Now in the case of lens, we have basically three actions. We have view, which is basically your getter. We have set, which is your setter, and modify. Modify is a setter, but with modify, you can also apply a function, specific function to what you're focusing on. So those are the three actions to remember. So let's move on. So now the optics by example book uses some terminology which is nice to know. So I'll try to show that. So this is the very first example which you also see here. So we have the view, which is our action. This is our structure. We have basically a tuple, and then the second member is also a tuple. So this is our structure, and then this is the path, or the path or the path will decide what you are focusing on inside the structure. So here the path has _2 and composed with an _1. Now this should give you some idea what it's focusing on. So one will focus on the first member of the tuple, and the second will focus on the second member of the tuple. Now one thing to know about lenses, lenses compose differently to your regular composition operator. So the dot function composition operator behaves differently to how lenses do. So we will learn why it's that a little bit later. So the first thing to remember is, since the order of composition here is different, what will happen is this will actually be the first thing to work. Let's say apply, or let's say I'm applying this function on this structure. So _2 will select my second tuple, and then _1 will select this. So that's why it is mentioning this is the focus. If it was regular function composition of how it worked, it would have been _1 first, which would have done 42, but then this wouldn't work because there is nothing second here. This is not a tuple. So the order of composition in lenses is different. So function composition works from right to left, but in lenses or optics, composition works from left to right. So this is one thing to know. So this is my action. In case of lenses, you have view, set, or modify. This will decide the path, and then you have your actual structure. The path will decide what we select inside the structure. So that's basically the way to read it. So coming back here, so if you see, if I run this, I will get hello as the answer. So let's similarly see a few other examples so that it becomes more clear. Here we have different view action. We have _1, then 2. So we will first select this and then this. So you can see the answer is 2. We have a setter now. The action is the set. This is a path. So second means this, and then _left means work only if it's a left. And since it's a left, we have old as the focus, and you can see we want it to be set to new, so this has been set to new. Moving on, now we have over as the action. If you remember, I said over can take a function. So let's see how this works. We have this. We are saying we are gonna taking to worded. So what it seems to do is worded will basically give you all the words. So testing 1, 2, 3 will be separated out. It will take the 2 traverses for walking over it, and then those 2 that are selected, those will have them changed to upper. So you can see it works out like this. Then we have a fold. So one of the things here is this is actually using a traversal and a fold, but because of the way the underlying construction is, you can actually compose lenses and folds and traversals together. So that's why you are seeing this. But so you can still use it as a lens as well. Why, it will become more clear once we look at the construction, but for now, just take it as it is. So we have over as the action, and then we have the traversal and a fold doing it. In here, we have fold off, we have both and each. So here fold off is our action. This is the path, and this is our structure. So what it seems to do is it will select both of them. See, it's a tuple, and then each member is basically list. So it will select both members of the tuple, and then inside it, it will select each member of the list, and it's doing a fold off. So it's doing a reduction based, and it has concatenated all because if you remember, for strings, the nature of fold or a monoid is to basically concatenate. So this is what you get. Though what it's doing is not so much the focus here as much as is you recognize what is the action, what is the path, and what is the structure. Okay. Is my microphone too noisy or something?
No, I think it's fine.
Okay. Okay, fine. So any questions till now? Is the way to decide what's your action, what's the path, and what's the structure is something you can read and decide? Is any example not clear before I move on? Okay, so let's move on. So after this, what I've done is, so the actual lens types are a bit complex. So the next few examples, what they will do is they will consider that we are not doing what is basically a polymorphic update. So basically, if my structure is an S, so if we look at a good example is, let's say this one. So basically, this is a tuple of cats. And here I have the end result basically has a different type at the third member. So this is what it's a polymorphic update. A polymorphic update is where you change the types from what the input structure was. So if this is an A and these are my A's, the end result is now in Lens terminology a D having B's. So that's the way to read it. But the first few examples that we will see will not be polymorphic. And when you see anything which has a tick, these are basically the non-polymorphic update ones. So we will first see just the simple type signatures so it's more clear. So if we, but I have also given the actual types. So for example, if you see the type of _1, it has this type. So this is pretty complex one to read unless you don't know what's going on behind the scenes. But the simplest one is this. So the lens tick basically says that I'm not considering polymorphic updates. And for the case of tuple, all I'm doing is I have a tuple of A and B. I'm gonna focus on just the A. So my this is A to comma B is the structure, which is a tuple, and my focus is gonna be A. Similarly, for _2, I will have this, but this will basically be B. You can see the actual types, and you can see also how it works out for the tuple A and a B. When you see a lens tick something, your first thing, this is gonna be S, which is the structure, and then this will be the focus. So in case of _1, my focus is the first member of the tuple. Now let's see the set and over. So the complex ones are here, and in the comments this is the simpler one. So I take a lens, so this can be, let's say, _1. I take the thing that I want to get or a set. In this case, it's a set. I want to set it inside my S. And since we are talking about non-polymorphic updates here, my end result is still an S. We have not changed the types. Over, as I mentioned earlier a bit, it can take a function. So we are taking a lens. We have a function from A to A. We are not changing types. If we are changing types, this would be an A to B. This is our S structure, and we are still getting an S. So if you run set_1x over this, you can see the first member has been set to S. And if you are using over, you can see I can apply a function on what I'm basically focusing on. So the first thing has become now 100. So that's the way view, set, and over basically works, and how you kind of read these things. Our action, our path, if we have a set, what to set, or if we have a function in the case of over, and then our structure. Your path decides what you're focusing on. Then we have some exercises which I have solved. There are simpler ones which you can go through later. Coming to how we now start using them. So, like I mentioned, lenses are primarily used in the case of records. So I have a simple record here. It has a name and an age. Now, if you see there's an underscore, I'll come to why we do that a bit later. So it's a simple record. It has a name and an age, string and an int. And then I want to do a lens. So let's see how that works. If you see the signature for lens, the simpler one, it's like this. So this is basically my getter, S to A. This is my setter, S to B to T. So, and then lens type. So I can supply a getter. Now, why is that? So in lens terminology, generally you will see STAB, where S is your input structure, A will be your focus. Depending on whether you are doing a polymorphic update or not, you basically have this. So, but in this case, let's say this is an A. So basically I have a S, I have an A, and I get an S. This is my setter. And since this is not the polymorphic one, you can see the tick here. And you can see the polymorphic signature, which is the full lens STAB. So now let's see how to build the lens part. So I'm assuming everyone knows how to do records in Haskell. So I'll just walk through. I have a simple age, get age. I'm taking a name, and it gives me an int. So basically I'm focusing on this part of my record, and it's just the underscore age field. Then same way for the set, I'm taking my actual name, the new age, and then I'm just doing this. So this is basically a record accessor pattern of how you do work with records in Haskell. And then coming to my actual lens. So this is my age lens. So I'm calling it num age. I'm considering non-polymorphic update, so it is a tick. And then this is what the library will give you so that you can build a lens. I'm passing my getter, and then I'm giving it a setter. You can see the types on top. I mean, the more polymorphic specialized types. The specialized types are here, and the fully generalized types are on in comments. So that's the way to build the lens. Any questions so far?
Is that the only way to build a lens?
No. So this is when you are writing it yourself.
Right,
Generally,
but
yeah.
from scratch, this is the only way.
Yeah. Assuming you are still using the lens library, basically you will use the lens function provided by it, and then you just give it your setter and getter, and then that becomes your lens.
Got it.
but we'll get to it a little bit later that you actually do not need to even do this. We'll come to it. But yeah, if you want to write your own, this is how you would do it. Okay. Same way, I have get name and set name, and this is my name lens. You can see the structure is the same, but what we are focusing on has changed. So this is my name lens, that is my age lens. And then if I want to actually use it, I just do it like this. So I've defined a simple example here, my name, and then you can run your lenses like this. So view, you can see it gives you the age. I can do a set. It gives you the new record with the age set. You can also apply the function over. You can also use a combination of set and view to make it mimic as over, but that's just for completion's sake. And then same way for the name. So that's all there is to using a lens. So now coming to how to automatically generate it. Generally, you will not write this by hand. So what you will be doing is, if you notice, I have at the top template Haskell enabled. So if you have template Haskell enabled, what you can do is you can just call something like this syntax, make lenses, tick tick, and then your record name. And the catch is that your record name should have to be defined like this. They come with underscores, so that your actual lens will come out with just the name. And if you see, you can see that's what I've done here. And you can see if I try to check the types, it gives me the lenses. I have not written the lenses for ship, but it automatically generates it. So that's how you would do it in actual project. But this was just to give you an idea. If you wanted to write by hand, you can still do it. You just need to use this lens function definition. Okay, so just some more example. And a few examples I have there. And now a lot of type classes, lenses also have laws, but they are pretty intuitive. So there are 3 lens laws. It just states what you would think should make sense of any getter and setter. You get back what you set. Setting back what you got doesn't do anything. Setting twice is the same as setting once. So these are the basic lens laws. And for anything to be called a lens, they always have to adhere to these laws. So that's the idea. I will not go more deeper into that. And I'm also skipping this last example, but if you are interested, this example is primarily about how you can use lenses to kind of get around the fact that even if some things have changed, maybe your record has changed or how you want to access it. So this example basically talks about having a temperature which is a Celsius, but what if you then wanted a Fahrenheit? So by using lenses, you could kind of, let's say, keep the API safe, so to speak of. So that basically completes the lens usage part. So anyone has any questions before I move further to how actually they work under the hood?
Ishan has a question in chat.
Okay. Why the ship and not ship? I didn't get the question.
I think it's in the auto generation. Yeah, you were on that page.
Yeah. So
Why
uh,
the single quotes?
this one. So this is template Haskell syntax for auto generating. I do not know why it has to be like this, to be honest.
So I can give a small answer to that. There is an echo, so it's. I think Sanchan, your mic is echoing. Okay, thank you. So just no, it's still echoing. Not sure if it's
So it's not me, I think.
okay. Oh, can you? Okay, great. Yeah, this is much better. Can everyone still hear me? That was actually me. So, what basically happens is that when you do a single quote, that's basically converting. That's basically passing it to an expression in template Haskell. But when you do a double quote, that's passing it to a type in template Haskell. So I don't know what make lenses does internally, but double quote passes it as a type.
Okay. Mm, okay. There seems to be another question. How do lenses compare to pattern matching? Okay. Uh, so you could pattern match on a record as well, but if a record is quite complex or nested, then pattern matching becomes quite unwieldy. So imagine if I have a record which actually has four other complex record inside it, or maybe even more, then pattern matching will be quite unwieldy and quite headache to work with. So with lenses, it becomes much easier that you can actually just go in any layer deep and either just get or set or apply some function. So yeah, you could pattern match too, no harm in that. But beyond certain level, pattern match just starts becoming more noisy, so to say. Uh, Lenses are more suitable for complex destructuring. So So pattern match you are definitely destructuring, but lenses is not necessarily for destructuring. Lenses is when I want to work with some member of some structure. I let's say if I'm talking about the simplest case, person, name, and age. I just want an age. I do not care about the rest of the structure. So lens will allow me to just focus and work with that particular member. I need not bother about the rest. So I need not even destructure it. Does that answer your question, Apurva? Okay. Does anyone else have some other questions?
Sanchayan,
Yeah,
so you say that we focus on only one member at a time. But what
right.
if a scenario like something where we need two members, like the values of two members, and do something with it at the same time?
Then
Oh,
you would need
yeah.
what would not be a lens, but let's say a traversal.
Okay. I don't know a traversal, so can you just
Yeah,
give me
yeah.
the brief?
So so traversal. Are you aware of traverse or the traversable type class?
Yeah, yeah.
Yeah, so it's kind of the same thing. What the traversal will allow you to do is select zero or more members of whatever structure you're walking through or you're working with, and then you can either just get whatever those members are, or you can also set or you can apply some function to them. But with a lens, you can only focus on one. If you want more, then you need to opt for a traversal.
Okay.
So that lens. So uh, let's say basically a list. If I have a list, I cannot use a lens to focus on a specific member of the list. I need a traversal so that I can walk through it and then, based on some criteria, decide that these are the members I want to work with. So for that scenario, you won't have a lens, but you need to work with a traversal. Lens will always focus on a single member of the structure.
And also the reason for that is pretty intuitive, because Lens also allows you to set values. So if you have a list and you set the values in a list, then you have to make sure that the number of elements match, right? So like intuitively, I can tell that setting is a different problem and a difficult problem with multiple elements.
Yeah, yeah. And if you start going a bit deeper and look at the types, uh, so you will see how the types change if you really want to do that kind of a thing, like you want multiple members. You cannot do what a lens gives you, or with what how a lens is defined. Okay. So unless there are more questions, I am moving on. So now what I'm gonna try to cover and talk about in the next one, a little bit over an hour, is how lens works in the background. So this can actually be a full 1 day class or a course, to be honest, like how it's connected at Functional Connect. But I will just cover the concepts at a high level, so that if you want, you can try and go deeper. But at least the concepts should still be clear. So what I'm gonna start with is, this is the Let's Rents repo. So this is from Data61, which you can look up on GitHub. It has 4 sets which cover, let's say, 4 different kinds of lens constructions. So it starts from the simplest, which is the get set lens, which is like just makes sense as the simplest one. Then it moves on to a different kind of a construction, just a slightly different way of writing things. And then we move to the actual one, which is used in the lens library, which are known as the Van Laarhoven lens, after the person who actually first came up with the idea. And then in the final part, we move on to basically traversals and folds, and also prisms. And here is where profunctors come in, because the way you define lens does not work if you want to work with prisms. We'll see what prisms are, but the construction has to be changed if you want a prism which basically works with some types. Lenses, folds, and traversals are primarily for your product types. So let's start with the first one, which is get set lens. Is my screen visible to everyone, or should I increase the font? I'm assuming it is visible and clear to everyone. So this is the way a simplest lens is defined. If you saw the lens type signature here when we were checking the lens function, you can see basically it's the same thing here. So we have we have a simple lens type, lens AB, and it basically is 2 functions, and A2, B2, and A. So here my structure is actually the A, my focus is B, and I get the same structure back. So this is my setter, and this is my getter. This is an A to B. That's all there is to that construction. And if you see, so assuming if you, this is the construction if you have, and if you just wanted to get your getter, this is all that you do. You can see the first is ignored because this is my actually setter. I have the getter here, so I'm just ignoring it and I'm returning my getter. Same way for the set, I'm ignoring my getter. I'm taking my setter. I have this type and I'm just passing it to my setter. So you can also see some examples are here on how they are working. So for this tuple, your first member is basically being set to 1 when you are giving a first lens. So this is in this repo, the terminology or the combinators are slightly different, but this is basically your first lens or what focuses on the first member of a tuple, and you are setting it. So this is what you get. So this is my set lens. This is the way of how I would retrieve a setter. Sorry, not a set lens. So you can see it's a pretty simple one. There is nothing much to do with it. You basically just define a product type which encapsulates having always to carry these two functions around. That's the basic idea. And then you have your laws, and then you have some various helper functions and rest of the things. But that's what your basic construction is. This is your primary, simplest, less construction that you can walk away with. Any questions so far before we move on to the next one? Here's are the two types clear? So the characters are a bit different, but so we don't have an S and an A and a T here, but that's the basic idea. So if you want to write it in the same way as what we are seeing from the lens library, it would be like this. So this is your setter and this is your getter. So let's move on to the next one. Which is what's the repo calls as a store lens. Here, the lens type is defined something like this. So the idea is, if you go back, the idea is if you see there is a pattern here. If you see there is a pattern here, the S to A is common in between the setter and the getter. So the idea is, why carry these two around and why not combine them? So it does something like this, where your store is defined like this. So I've just copied it here so it's easier to see in one shot. So the store is defined like this. Your data store SA is a type of store S2A and then an S. So now, if you're wondering how does this convert to our previous presentation, all you need to do is just unpack it. So if you see, that's what I've tried to do here. The earlier representation is here for your convenience if you want to see. So we remove the lens as the wrapper. I write the store B2A explicitly the way it's defined. And then I drop the store wrapper as well. And then if you see, this is A to B to A and A to B. So that's how basically you have the setter and getter being hidden inside the store data type. So that's the basic idea, that since we do not want to carry around explicitly the setter and getter, and they share a common pattern, we can hide it in what is known as a store. Now, there is some maths behind it if you want to look it up, but that's not our concern here. But there is also some maths behind it of how, why it comes like this. But for our cases, that's not a concern. So if you just unwrap it, it basically works out to like this. And if you actually work through the exercises and see how get and set is implemented, you will it will be more clear. But I'm not covering this in more detail because this is not what it's actually used in the Lens library. So, but just for cases, purposes of completion, and if you ever decide to work your way through this repo, it might be helpful. Any questions so far? Okay, I'm assuming not. So let's move on. So now let's come to the interesting part of what is our the representation that is actually used in the lens control lens library in Haskell, which is done by Edward Kemet. So here the way lens is defined is something like this. Now this doesn't make much of a sense of how it will encompass your setter and getter. So let's try to work through it of how you would do it in the repo. Now here there are two things. One is you can try to understand it by actually seeing how get and set, how you would do the get and set for this particular definition. So this is what is done here. The other way is the let's say the intuitive way, which may be the guy Van Laarhoven, how he found it out. So let's see how it does the getter part. Okay, so I'll just comment this out. And I'm going to slightly this. What I'm gonna do is I'm gonna start GHC IDE so we can see the type holes thing. Okay, so it has given us a type hole. It is this one. And if you look at it, it says found a hole, and then the key part to look here is this, the relevant bindings. So R is our lens, which is what we are destructuring on the left. S has the type S, and then it just gives us the type of the function. Now, what we are going to do is I'm going to do something very specific. But before we do that, let's have a look a bit more at the type. If you notice, we are saying for all f, functor f, and then it is a to fb, s to fp. Now, the for all, for people who don't know, it's basically what's called existential types or signatures in Haskell. What it basically means is whatever you have to the right of for all. So basically, for all of functor f means whatever signature you have to the right of this constraint should basically work for all functors, not just a specific functor. So it doesn't matter what functor you have across whole of Haskell, it should work for all of them. That's what basically it means. So keeping that out of the way, so this basically says that my f has to be a functor. Now the interesting part here is if you change the functor that you apply or you give to this signature, you can do different things. So one thing that changes is depending on the functor you apply, you can retrieve your setter and getter. The other part is if I change the constraint. So if I change what my f is, so here the constraint is that the f has to be a functor. But if I now say that the f also has got to be an applicative, what I get is basically a traversal. if you look at the signature of traverse, let me, actually I don't have it open. So let's go to Google. So my traverse. So you can see this is pretty much the same with some changes here, but you can see the applicative constraint. So if you change this constraint to be an applicative, you will get a traversal. So instead of a lens, you now get a traversal. Same way, you can also get a fold with a different constraint. So just by having the same signature but a different constraint, you get a lens, or you get a fold, or you get a traversal. So that's what basically makes this a lot powerful. Just by changing the constraint, you can get different things. And what happens is they are composable. So when, let's say, you want to do composition of a lens and a fold, or a lens and a traversal, you basically have applicative and a functor constraint. But if you know from Haskell, applicatives are also basically, they also have to be functors. So they kind of unify at that level, as it's called, or basically they combine down to your one single constraint. A union of functor and applicative basically gives you the power of the applicative. So just by changing the constraint, you get different things, and you also get composition. So that's the idea behind it. So when you see, let's say if you see a traversal, lens traversal, so I have this open here. So let's see how a lens traversal looks like. So you can see this signature. So my lens STAB now has a type traversal STAB. This thing is still the same, but you can see this has changed. This is now an applicative. And you can also compare it with how traverse works in Haskell. The traversal type class works in Haskell. So just changing the constraint basically gives you different things. So that's one funda behind it. Now coming to the other one. So what happens depending on the functor I give it? So let's say what I'm gonna do is I'm gonna give you a const functor. So the type for const is defined here. Sorry, this is my type for const. What I'm gonna do is I am gonna write it like this. The reason I'm writing it like this and not kind of the point free style is then I can actually look at what the middle type is. So I'm just gonna do this. And you can see the type of RC. So R was my actual lens, this one. And now if I give it a functor, which is a const, my const is basically this. This is what I get. So it has become, so you can see its type. So what I gave is a const functor. So basically what I gave it is, I have given it this. You can contrast it with this here. So my f has been specialized to a const a. And since this is now applied, the rest has to be my return type. So RC has to be this S to FT, but F is now specialized to S const AT. So we have RC now. Now, if you know const basically what it does is, if I have a const AB, it basically just ignores my B. And you can see it's basically for all B. It doesn't care what B is. I'm going to just ignore it. So this T is something we do not care about. So what we have is const AT. Now we only have this now. It's not, there's nothing else to work with. And since it's a function which goes from S to something, let's see what happens if we just apply S to it. So what I'm going to do is I'm just going to write RCS. And let's see how it works out. So it gives me something. It tells me it cannot construct the infinite type a to const at. So let me do something more. Since my RC I have applied to S, my return type should now be const at. So since I do not care about the t and I want the a out of that const, what I can do is basically I can say get const. And okay, I have those changes on the second time. So let's start compiling. Now all is good. So now we don't have any errors. That means it's all correct now. So how it worked out is I gave it a const functor, and then what it gave me is s2 const at. Since f was specialized to const at, I applied an s, which is here. So I get const at in the end, but I just wanted an a out of it. So I did get const. If you check get const has basically this type, const a b to const a. And now that's what basically your getter was. You got the a out of it. Any questions on how this worked? Okay. So I will go to the setter. So I will not work this out because it will take a while. So here, if you see, I've used an identity. So what these two things tell us is, if you have a lens, and if you're wondering how does this even encompass your getter and setter, by deciding a particular functor for it, you can get your getter or a setter back. So if I give it a const, the const functor, it will give me my getter, which is, if you see the return type is a. And if I wanted a setter, all I have to do is use identity. So deciding which functor you supply to it, or basically this specific thing which you supply, a to fb, what you supply as the a to fb function decides what you get out, whether you wanted the getter out of it or whether you wanted the setter out of it. Now that's going with the types. Now if we wanted to work out the intuitive way of doing things, so let's start with the setter. So this is my setter, S2A. My structure is S. It has some A inside it. And what can be done is, this can be converted into this form. So just let me close this, improve this. So from S to A, I can go from an A to R to S to R. Now this is something called as a continuation passing style. Now how does exactly this come about to be? So if you look at the documentation, so let's go to the documentation of our getter. So in this particular case, it says this thing, this function is basically isomorphic to an arbitrary function S2A. Now, what does isomorphism mean? Isomorphism means basically that you can think two things are equivalent, or you get what is known as a invertible function or a bijection in maths. So in the simplest case, it means that if I have an S, I can go from an S to an A, or I can go from an A to S. So basically it's invertible. You can go back and forth. That's what isomorphism basically means. Now it says that this type is basically isomorphic to this S to A. Now, how exactly does this happen? Also, for purposes of completion, let's say I have the same kind of signature that I have here. So I'm gonna say for all R, so that it's basically for all R and not just not just some specific R. For any R, this should be true. Now, how exactly does this work out? So this is, so your F, okay, let's say this is my F as the type S2A. My F is basically, okay, and let's call this FCPS. Now this one I'm actually using as Anupam kindly explained me, which is how I finally got it. But initially it was not clear how exactly are these two equivalent. So maybe once I finish writing this, maybe Anupam can chime in if it's not clear to someone, or maybe I'm not able to better explain this. So I'm gonna use this symbol for, let's say, type equality kind of thing. And what I'm gonna say is my F is basically equivalent to FCPS ID. So FCPS is something like this. This is the way of writing it, how you would do if you are writing it kind of as in lambda functions. And it's basically equivalent to this. Now, in case you're wondering why it's called continuation passing style, it's very similar to the concept of a callback in other languages. In fact, it's basically a callback. So you basically pass a continuation or a callback, which is my A to FP. And the only way I can do anything else with it is, in this case, because here we have a bit different types. So I have a continuation A to R. I have my S, and I'm getting an R in the end. The only way I can do anything with this is if I pass a continuation A to R, and then if I want an R out of it, I have to apply A to it. There's no way, there is no other way of actually being able to do anything with it. You have to use the callback. And if you remember, basically we came from this part, S to A. So I'm going to give a continuation or a callback, and it's going to call that callback. It's going to give a, so in this case, my C, if we were actually writing out the types, this C is basically my A to R here. And you can see the A to R, how you are going to do anything with it is, so okay, let me expand it, it's a bit better. So my C is A to R, and my F is S to A. So to do anything with it, I have to apply A. I will first do my F, since that's how function composition works. S to A will give me an A, and then this gets applied to my continuation, which is A to R, and then that's how you get an R in the end. So that's how it basically works out. So you start with a simple setter, and you kind of write it in the CPS style and get this. And then let's say here my R is same, but what if I wanted to change the types? So I can say, instead of having just R, I can say I have an FR. I go to the functor constraint, and then I can go actually one step further and say that so this is our non-polymorphic update case. I can say that I want polymorphic update, so I will just make it an A to FB. S, and this becomes an FT. Since you change the type, in the A which was inside S becomes B, so the S has now become a T, and you have this functor thing now. So that's how you basically start from an S to A, and then you end up at the signature. Okay, so that's quite a bit to swallow in one shot. So anyone has questions? On either of how you get a getter and setter out of the lens signature that you see, or how that lens signature came about to be. I'm gonna wait for 2 minutes just to give my throat a little rest. And in the meantime, if anyone has any questions, they can ask in the chat or holler. Hey, Manas, Anupam or Arun, all still good?
Yep.
Okay. How about you, Manas? Are you getting stuff so far?
Yeah, not everything, because there is we also use lenses in OCaml. Hello, can you hear me?
Yeah, I can hear you.
Yeah, so I've never bothered to know how the internals work. Actually, I've just played with the idea of lenses. It's called accessors there, and
Mhm.
yeah, this is all new and interesting. So I'm just listening.
Okay. Yeah, so lenses are basically the accessor pattern. They subsume the accessor pattern in some ways because they're more powerful.
Right. No, I think the library is
Yeah.
just called accessors, but in fact,
Okay.
the entire implementation and the whole idea is in fact coming from Haskell. At least that's what the README says. So
Okay.
I've just used it and I've never bothered how it works. So this is
Okay.
all interesting. I'm just listening in, and there are a couple of
Sure,
things
sure.
here that are slightly yeah. There are many new things here, so I'll just listen in today.
Sure. Okay.
Sanchayan,
Yeah.
in the last line that you wrote, the type signature we have, what is the T here? Is it anything or is it some derived type?
So T is, so you can think of it as S as the starting type or your input, and T is your final output or a target type. So let's say if my we saw the person structure, right? So we saw this, right? So this is your S. Imagine if I'm changing the int to be a string now. So basically I'm saying just pass show to it,
Yeah.
right? So then your output structure will be name and age, but the age will now be a string type. So the type has changed. So that's what a T is. So it's basically just a type. It signifies that the type has changed from the
Okay.
initial one, which was an S,
So
or in the case,
it's like the replacement of type S now. Now it is T.
yeah.
Like
So it's
yeah.
a new structure or a new type now. It's not the same old one.
Okay.
So basically, I'm changing the types. So to be very specific, let's write it down a bit. So in this specific case, my A to B is int to string, which I can do by doing show, passing a show to my over. So my original S has the name, which has a string and an int. Since I have applied a function which is going to change the type of what is inside S, now S will not be an S anymore since the type has changed,
Yeah,
and it will
got
be
it.
string.
Got it. Thanks.
So that's what it is. So STAB is basically the general nomenclature in the Nens library, where S is your input type, T is your output type, A is what is inside the S, and then since we went from A to B, S now became a T. That's the idea. Does that make sense?
Yep.
Okay. So any other questions? Okay. So I'm assuming that you at least are getting something out of this till now. So what I will now do is, so this is one way of constructing it. So this is what's called the Van Laar-Hoven lens. This is what the guy called Van Laar-Hoven came up with for the first time. And that's why it's called Van Laar-Hoven lens. This is a particular construction. It's also this particular CPS style, or you can also call it, which he called it, functional references, if you look up the original article. So that's what it is. But there are other ways to do it. Now, before I can show you the other way to do it, so we talked about functor here. Now we need to see what a so this functor, or the functor that you mostly work with in Haskell, or maybe let's say even PureScript and all, this is what are known as covariant functors. So there is also something called as a contravariant functor. So let's see what a contravariant functor is. So this is just a small page. I just did it for completion's sake. So if you see a functor signature, so a functor class is basically fmap, which is the primary method that is has, and it is something like this. So this is how the fmap type signature looks like. Now, if we look at the contravariant one, so which is now contramap, you can see the type has slightly changed. Here we went from an FA to FB, but here it's now an FB to an FA. Now, and we still have the function. So this might seem strange as to why are we even doing this. So the intuitive understanding behind having a contravariant functor is, or having a contramap is, fmap, or what functors do basically, you consume something. Sorry, the idea behind fmap is you produce something. So you take an A and you spit a B out. In case of contramap, the idea is you consume. You do not produce, but you consume. I think this becomes more clear when I jump to what is pro-functors next, but let's look at a simple example. So I have this predicate A here, and it's basically a function which is A to bool. And I have this type, which what basically does is it takes the arguments in a reverse order, but it's basically this function. Now, if you were to write a contravariant functor instance of this is how it would work out. Now, if so, let's try to write it from the start. So what I will do is I will comment it out. I will say contramap ft. I know I want an op. and I'm gonna do this. I'm gonna use a typo. I'm gonna just run it. It gives me this. So I don't have much. I just still have the F. What I want to do is I want to get this one out. So I'm gonna write it in a bit bit more explicit ways. Though actually you could do it in simpler point-free form. So this is a Haskell record type kind of thing, which is what's happening here on the right. So what all I'm doing is I'm calling getOp on this G, and which is my this it will become to this type. So we have the binding here now. So I have my G, I have my B2 and A, and I have my AF, which is the original function given. Now, and the whole says I want an A1 to an A. So this is my final thing which I require. This is what I have. We can ignore G at the moment. We don't care. We have got out of it what we wanted to. So I have basically these two functions, B to A and A1 to B, and I want an A1 to A. So all I can do is basically compose them. So basically A1 to B, and if you if you apply A1 to F, you get an B, and to that you can apply B to A so that you get an A, which is our final function type. I will just do this. We don't have any more errors. So if you see this thing, what it's doing is it's applying the F first, and then it's applying whatever was inside my op. So this should give you some idea that what contravariant is about is, let's say if you have, let's say I have a function which can go B to C, but I don't have B's. What I have is A's. What I have is A's, but I can go from B to C, but I only have A's. So I cannot do anything with this function. But if I had a function which went the other way, so if I can do some kind of a pre-processing, then what I can do is I can give the A's to this function, and then I can use this one. So this is basically what my F map will do, and this is basically what my contra map will do. So F map, or the idea of a functor, is basically about producing. So it produces the C's, and the contra map, the idea is I can consume A's. So I can have something in between. I don't know what it is. I don't care. But let's say I can kind of make a processing pipeline like this. So my contra map functions will pre-process, and my F map functions will do post-process. That's where the contra comes in. Of course, you need not always have an F map. You can just have a contra map. So the contra map is basically about pre-processing. Now, to give you some idea, so there is a library called colog. It's a logging library. Okay, so I'm gonna search for a contravariant instance in it, and its log action type is basically my primary type in the colog library, which basically takes message, and then that M, let's say, is basically the simplest case is just print it to the console. If you look at the instance, it has a contravariant instance. So the reason it has a contravariant instance is, if you think about logging, so let's say the simplest log library can always do strings and then print to the console. But you might not always have strings. You can have, I don't know, anything, any complex Haskell data type. So a control function can pre-process it. So let's say I have a if you have done Haskell, you know there are various string text, lazy byte string types and all that, and sometimes you need to convert between them. So let's say I have the more efficient text type, but my Colog library, let's say for purposes of simplification, can only take a string. So what I can do is, since it is a contra map instance, I can convert the text to string, and then my Colog library will work with the string. So that's what basically contravariant is about. You kind of do the pre-processing, so it consumes, while the fmap is the other idea that you produce. Any questions so far? Okay. So now the next construction actually uses both. So it takes a functor and it also takes a contravariant. And when you have both, what you get is what is called a profunctor. So this is my profunctor class. It has what is called as a tie map. And you can see this is my signature. So if you pay attention to the types, ignore the P for now. I have a function B to A, but here I have a, basically I'm going from an A to a B. So this is my contramap. And this is simple. This is our regular functor case, since I have a C to D and I'm also going from C to D. So what a profunctor has is, it has a function which is contravariant in its first argument and a covariant in its second argument. So profunctor is like a processing pipeline where you can have a function in the middle and then pre-process it and then post-process it. So the pre-processing will be done by your contramap, which is this, and your post-processing will be done by a functor, which is this. So that's the kind of the intuitive way to think about profunctors. And if you look at the function signature, so a profunctor is basically also a generalization that if you look at this instance, so we had A to FB, right? So our P is basically this. So this is a special case. Our P is basically the function. If you write it profunctor style, it is basically PAB. There your P is nothing but your function. So once you think about this, so then the idea of why profunctors exist becomes more clear. It's one level abstraction up. You had a functor, now you also have a contravariant, and you can do much more with it. And the P or the profunctor basically generalizes it. So that's what you have. So when you see a PAC or whatever, all it means is there is some kind of a relation between A and C. So the complete way to read this would be, given a contramap function B to a covariant functor function C to D, and some kind of a relation between A and C, I can go and have a relation between B and D. And if you focus on the actual function instance, that's what it does. So you have the H in between. My H is actually PAC. And what we do is, we have the G, we have the PAC in between, and then we have the F. Now, if this is not clear, we can look at, there is a nice repo called Don't Fear the Profunctor Optics. Yeah, this one. So this has some nice diagrams which make clear what profunctors are about. So let's have a look at diagrams if that was not clear. So this is how it is. So things are all written here. So here just this letters are a bit different, but my profunctor is this one, PAB. So this has been termed an edge, and I have an A tick to A, which is this. So like we said, this is my contour map stuff, which you can see here. Here it's A tick to A, but here it's going from A to A tick. So this is my contour map part, and this is my regular functor part, covariant, B to B tick. So this is how it looks like. So I have some relation in between. I have my contour map. I have my functor, covariant one, and I can compose this full build thing. So I give an A tick. I can, with the F, I can go from an A tick to A. My H was from A, some relation between A to B. It did not matter. And then I had my G, B to B tick. So you finally get a B tick. So this is basically a full value transformation pipeline. So you had this, you had some kind of relation between A and B. In the simplest case, if you are talking only about a function, this is basically A to B. But now that you have a contour map and a covariant functor, you can go from, instead of just having an A to B, you can go from an A tick to a B tick. So this pre-processes and this post-processes. And if you want to separate it out, what DIMAP calls it, what DIMAP does, you can only have the L map. So my covariant functor part becomes an ID, or I can only have the R map. So I can only have the pre-process, or I can only also have the post-process. So that's how functors work out. And that's how you get pro-functor lenses. Now this is a different construction compared to what we had earlier in here. Now, why would you care about this construction is the question. So the reason we care about this is, if we only have this construction, we cannot have prisms. We can only have lens, folds, and traversals. Since we only have a functor, and functor can be your applicative or a functor, and accordingly you get a traversal or your regular functor, or you get something in between, which is a fold. That's all you can do. And the only thing it will allow you to do is work with product types. If you want to work with sum types, which is basically, so the simplest product type is my tuple A comma B. My simplest sum type is either AB. So, or actually bool is the simplest sum type. So true or false. So you cannot work with sum types. You need prisms for that. So if we want prisms, we need to have profunctors. Now, why is it that? So why is it that you need profunctors for prisms? So for that, let's take a quick detour of why do we even have, or what basically are even product and sum types. So they have a slight analog in the algebra, where the reason it's called a sum or a product is because that's what the, let's say, inhabitants of the types can be. So in case of a tuple, the number of inhabitants, or if you remember from our old math days, what we used to call cardinality of a set, it's the cardinality of a product type like A comma B is basically A cross B. And the cardinality of a sum type, either AB, is A plus B. That's how this is a sum type, and that's why this is called a product type. So that's the idea behind it. And so now, how does it apply to profunctors? So the way it applies to profunctors is, let's look a bit at the types. So, Let me show you another library. So how does it exactly correspond to a profunctor? So if you think about product and sum types, so let's say I have an S. Let me open this scratch pad. So let's say I have an S. The reason it's called a product type is we can decompose this into something like this. So I have an A and the rest of the type, whatever that might be, which let's say that's a Q. So this is the way basically the decomposition happens. Or if I'm saying my S is a sum type, the deconstruction will be something like, since either is what your tuple is, I have something like this. So A comma Q. No, that's not right. Hmm, yeah, it's either Q. So this is the way the decomposition will be. So we only care about the A, and the rest is basically whatever is remaining. So in case of a product type, it decomposes into a tuple. In case of a sum type, you have something like this. Now, if you look at the profunctor classes, it has something called as a strong. Forget of what it's called strong. If you look at this signature, you can see I had some kind of a relation between A and B, and it took that and it gave me a relation between A comma C to B comma C. So our C is basically Q here, or whatever you want to call that character, it's irrelevant. So what the profunctor does is profunctor can decompose along these lines. Now this is not possible with a functor instance. Now, why is this not possible is because we'll have to go a bit more deeper into profunctors than what I can cover here. But for now, I'm only focusing on the type signatures. So if you see the type signature, the for the products, the profunctor can allow you to decompose to A and Q, and it can do the same for your sum types as well. So I should have the sum type here. So in case of sum type, it's called a choice. And in case of a product type, it's called a strong. You might see other nomenclatures. For example, I was showing you this, right? Here, the strong is called a Cartesian. Cartesian comes from the Cartesian product in maths. And the choice, it calls a co-Cartesian in this link, but the idea is the same. The signatures are the same. So you can see the choice gives you a decomposition along a sum type where you decompose between an A and a C. And if you look at left and right, you can see that you had a relation between A and B. It took that and it only changed the right part. The left part is still C. Same for the left, you can see the left has changed, but the right has not. Same way for the product also, it can be seen that _1 only gives you an A to B. It ignores the second part, and the same way for the for the 2. So the profunctor will allow you to do this, which is not possible in the case. So profunctor can still do lens, but this choice part is not possible in case of the Van Laar Hovens representation. That's why you come to the profunctors. And if you see the lens library, so let's have a look at the prism part. You can see the choice constraint here. You can see this has slightly changed. So instead of A to FB and an S to FT, you now have a generalization where it says P is my choice, which will be a profunctor, and it has generalized from your simple function to this. So that's why the profunctors come into the picture, just to cover a small part of it. And if you look at other libraries, so for example, there is also a library called MicroLens, but the MicroLens does not give you a prism. And the reason it does not give you a prism in Haskell is because the profunctors package is not part of your base, the base standard base, which is in Haskell. But if you see here, it has a dependency on profunctors. So that's why, for example, if you only want this lens, folds, and traversal, you could only use MicroLens. But if you wanted to have prisms, then you need to move on to have profunctors. And the profunctors are much more powerful since basically from the type, you should be able to see that they are generalizing the function part. So basically, previously we just had this, my arrow, but now it can be much more than that. So this becomes more powerful in what can do, and then you can branch out to prisms and much more. So that's how this comes into picture. So you went from a functor representation, sorry, that wasn't this, which is this part, to having contravariant, and then finally getting profunctors. And if you see the pure script lenses, that actually uses a full profunctor representation. It does not use this. It does not have a Van Laar style. There is also like a experimental, just someone wrote a pure profunctor style lens library called MesoLens, though it doesn't have as much combinators or useful stuff like the lens library, but as such the concept is complete. So you can, if you go down that part, you can see how the representations work out in this profunctors. Now, the one final part I want to cover is we talked about why lenses composed in a different order than your regular dot composition operator. So let's say I have a lens STAB. If you see the actual type, in the end, what you get is basically S2FT. Now imagine you have another lens, which let's call UWST. What you would get is basically, so its input, if we write it out, will be, so this was the output of my lens STAB part. And the input of this will basically be, if you see the types, the input, this will be basically S2FT, then my U, then my FW. And okay, let's, this is already written. Lens STB is what we have here. So you can see that lens STAB gives me S2FT, and another lens UWST basically takes S2FT. So when you want to compose this, so let's say I want to compose lens STAB with, so okay, no, so it should be like this. So when you want to compose this, it will basically be like this. Since the first one gives you an S2FT, and that is what this one takes, you can just compose it like this. So this order of composition is different to how your regular dot operator composes. So for example, the dot operator composes differently. If this were a lens, the order composition is F dot G. And the reason this is coming is because of this particular signature. This way of writing the continuous passing style is what is giving you a different order of composition compared to what your normal dot operator gives you. So that's the idea behind having a different order of composition. So I think that's what I wanted to cover for this talk. I know I covered quite a bit and quite a lot, but yeah, so that's it from my side. So let's have questions.
So apart from lenses and we covered lenses in this one,
Yeah.
and you mentioned prisms. What else is there in the library?
So we have the primary ones are lens, fold, traversals, and prisms. But you have quite a bit more for some. For example, if you remember, there was one example of a biplate. So there is
Right.
something called as biplate, uniplate, and multiplate. And that part I have not covered, but that's a bit more advanced stuff. So there is that. And then the other things basically is a lot of helper functions. So for example, you can use lenses on, let's say, exceptions. So for example, you can see here the exception lens. You can also use lenses on state or readers. So it should be somewhere down. So there are a lot of helpers that are available, but the four main key things are basically lens, fold, traversals, and prisms.
Right. Okay.
And one nice thing to look at is basically this hierarchy of what you have. So
I'm
you
not sure if this
start.
is nice. This is pretty scary when I looked at the page sometime back.
So this is nice once you get to a certain point, but it's nice in the sense like you can just see what's there at the top and what you will get from the library. So we have folds, we have getters and setters. So you can say they are part of the same point or something like that. You have traversals and then you have prisms. ISOs are basically about isomorphisms, which I briefly talked about. So basically about being able to have invertible functions and that kind of a thing. And then you have a slightly more specific equality. So, but that's what you get. So this is the full picture. And then the rest are basically helpers of what. So for example, I can have lens on state monad, those kind of things.
Got it.
We have the questions in the chat. So no questions? Did everything go on overboard? Oh, silence. That's bad.
Can we have like a follow-up session on the other parts of lenses that we haven't covered in some time?
Sure. I plan to have folds and traversals at some point. Maybe not too soonish, but probably sometime in April. And then prisms as well. So I will definitely cover them in follow-up sessions.
Cool. Sounds good.
So no questions. Okay, and I think I went quite a bit overboard.
Yeah, the lens is a pretty heavy topic. I've tried to learn lenses for quite a while now. I just need to spend a lot of time dedicated to it and trying to actually use it in real projects. But
Yeah.
I don't blame people if they find it hard to understand. This is very
Yeah.
dense and very deep,
Yeah.
right?
So one thing, like I said at the start, is if you just want to use lenses, you did not care about any of these things. You can just say you have your record time. You can do make lenses, and then you start basically just using them. You have your view set over, and that's pretty much true. You need not care about whether it's a functor in the under the hood, or whether it's a contravariant, or whether it's a profunctor. So none of that really matters if all you want to do is just use it. But yeah, so but it is quite interesting under the hood, so that's why I covered it. But the next sessions when I take, they will only focus on usages, and that will be much shorter.
Cool. Also, with Lens and these other things, the diagram that you showed, Sanchan, I think it also means that they compose really well. So
Yes, yes,
so the all the arrows, these are how you can compose them, right?
yeah.
So
So
if
you
you can
can,
compare,
yeah. So you
yeah.
can
So
compose a lens with a traversal.
right, right, which is fascinating that it
Yeah,
actually works and the types match. And so when you're in, so I've worked with code bases that use lenses, and usually working with them is very simple. You just
yeah,
follow
yeah,
whatever is being done, and it makes sense as long as you don't try to understand exactly how it's working.
yeah,
It just works fine.
yeah. So, for example, like at work, we use this library called Gogol, which is with all Google services things, and it gives quite a bit of lenses to work with. And, or, for example, if you're working with ASON, basically JSON types, ASON has something called as ASON lens, and it's very much easier to work with if we start using the lens stuff. You can just your JSON can be any nested deep, and you can compose the lenses, and it will pull the data out. So if people want to like start playing with how to use it, I will suggest just use ASON lens. Start with that, because I think a lot of probably people in the today are from, let's say, I'm assuming maybe that's not true. Let's say I come from the web background, or maybe you need to do JSON deserialization at some point. ASON lens is really nice to work with, and you can just have any kind of complex ASON type and just be able to like pull a particular thing out of it. Just
Right.
one example.
Yeah, the JSON accessor functions are wonderful. I've worked with
Yeah,
them, and they're pretty nice.
yeah. Or even let's say if you're working with HTTP, and let's say I have a library called WREC. It also gives ASON, or if I have lenses, I can just there is a lens called response header. I can apply that lens. I can say view response header on my response, and I will just get the headers out. That's it.
Right. Nice.
So just if you want to use them, no worries. It's really simple to use, so you can ignore a lot of the other stuff that I cover. But if you ever wonder, especially the composition part of it is really beautiful once you start using it. The way it works out is all the things that I tried to cover today. So if there are no more questions, I will hand it to you, Anupam, to kind of, let's say, give the ending note, so to say. And yeah, that would be from my
Sure.
side.
Yep. Thanks, Sanchay. This was a great session. Arun had a nice comment that we should do some kind of a clap or like something to sync the video and the audio together, because today we are recording them separately, and hopefully we'll be able to sync them together. So, Arun, are you still online?
I think he may have dropped off.
Okay, so I'm not sure how we can exactly sync. Okay, I have an idea. Maybe what we can do is I can record. Yeah, this will work, I think.
Yeah, let's see. Hey, Anupam, are you still there? Okay. Okay, so unless someone has more questions, then we will close for today, and I will post my notebook links on the Telegram page, as well as people who kind of RSVP to the meetup event page. I will also post it there, so you can see the notebooks. There are also two readmes. There is one readme which has links on all the posts that I refer to, kind of compress this information and understand everything that I spoke about today. And if you are more interested in continuation passing style and those things, it's in this readme. And the rest of the notebooks that you see basically correspond to chapters of the optics by example book. So you can just refer the examples also if you want. So if you have any more questions, you can reach out to me on Twitter or on the FPMCR Telegram group. So yeah, that would be it from my side.
Can anyone hear me?
Yeah, we can hear you, Anupam. At least I can.
Okay, great. Sorry, my phone battery ran out. I was on audio on my phone because I was recording the screen. Yeah, so okay. So yeah, so I switched off the recording. Thanks, Sanchan, for a
Sure.
great session, and we will have more lens sessions in the future, right? So, and I'll try to sync up the recordings and post them on the PNCR group so everyone can access it.
Yeah. Okay then.
All right. Thanks, everyone.
Yeah. Good night for the day. Bye bye.